All right, everybody, welcome back to part 2 of 9.3 Significance Test for Means. We're going to run through these last two examples. The first one is another one-sided test, but example 3 is a two-sided test. So if it's been a minute since you've looked at a two-sided one, you may want to hang in there for that third example with me. All right, so for this example 2, it says the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 30 randomly chosen locations along a stream. Here are the results in milligrams per liter. The X bar is 4.77 and the standard deviation, or SX, is 0.939. An average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do the data provide convincing evidence at the alpha equals 0.05 significance level that aquatic life in the stream is at risk? All right, so the average is below 5. So we've got enough evidence to go through and work the test. But let's go ahead and take a look at each bit. All right, so for our parameter, we're dealing with mu. And mu is the true mean level of dissolved oxygen. We knew that was going to happen, didn't we? Try that again. True mean, seriously? Apparently we've got it in 3 different places. There we go. I give up. Level of dissolved oxygen in the stream. And we know our statistic is our X bar, and it's 4.77. So for our two hypotheses, our null hypothesis would be that we're good, that it's at 5 milligrams per liter. And our alternate hypothesis is that it's not okay, and it would be less than 5. And then our alpha is 0.05. All right, so that's our state. All right, for our plan, this is a one sample t-test for means. All right, for the conditions, it's still normal, 10%, and random. So for random, they tell us it's randomly chosen. All right, so that one's good. For 10%, we're assuming that 30 is less than 10% of the locations along the river. Or the stream, sorry. And then for normal. All right, so it doesn't say that it comes from a normal population, but our sample size is 30, and so that works for our central limit theorem, so we don't need to graph it. And at this point, we couldn't anyway because we don't know our data values. All right, but because of that, all 3 of those, we're good to go. All right, so jumping down to the do. So our formula is our test statistic equals our stat minus our null over our standard error. All right, so our test statistic is t, and it's X bar minus our mu over Sx divided by the square root of n. Okay, so plug in those numbers in. That's 4.77 minus 5 over 0.939 divided by the square root of 30. And when I mash those buttons in my calculator, I'm going to end up with negative 1.342. All right, so that's my test statistic. That's right here. All right, now to draw our picture. This is a t distribution, not a normal distribution. So for T distribution, we just have to label with our degrees of freedom. So we had 30 in our sample, so 30 minus 1 would give us 29. Our mu was 5, and our average, our x bar, was 4.77. So that's where we're shading. We're shading below. And to find our p-value, then we've got to put this in our calculator. And so this is our t-CDF instead of norm CDF, because we're dealing with a t distribution. And that's our lower, our upper, and our degrees of freedom. So our t-CDF, our lower is going to be negative 9999. The upper, this is why we found our test statistic, so negative 1.342. And then our degrees of freedom is 29. So over here on our calculator, that's menu, number 6, and then number 5, and then t-CDF is also number 5. So our lower bound, you can make it negative 9999, or you can leave it as negative infinity. It's fine either way. And then our upper bound, like I said, was our t-value we found, negative 1.342. And our degrees of freedom is 29. And that ends up giving us, for our p-value, we get 0.0950. All right, so now we got to decide, are we rejecting or are we failing to reject? Well, 0.09 is not smaller than 0.05. So in this case, we have to fail to reject. So we fail to reject our null. Because our p-value is not smaller than our alpha. We do not have convincing evidence that the stream is not healthy. Sorry, I'm going to use their wording, that aquatic life in the stream is at risk. Apparently I'm going to fight with the pen for a minute. All right, cool. So that was another one-sided test. We shaded to the left because our alternate hypothesis was a less than. If our alternate hypothesis is greater than, then we're going to be shading to the right. All right, so that, like I said, was a one-sided hypothesis. And so for this last one, we're going to be dealing with the two-sided. If you feel confident and you want to go for it, go right ahead. If you'd rather sit with me and work through this one together, that's fine with me too. All right, so in the children's game, Don't Break the Ice, small plastic ice cubes are squeezed into a square frame. Each child takes turns tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. The machine that produces the plastic cubes is designed to make cubes that are 29.5 millimeters wide, but the actual width varies a little. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The Fathom output summarizes the data from a sample taken during 1 hour. All All right, so before we start looking at the numbers, just in case you've not ever seen this game before, this is Don't Break the Ice. I used to love this game. And so what you do is you put your penguin in the middle of it, and you tap the bricks and the pieces of ice, and you keep hammering, and the person that hammers the ice that makes the penguin fall down loses. It's silly, but it's a fun one. If you have youngers or brothers and sisters, you may have played this with them. But if you've not seen it before, that's how it is. You flip it over, you line all the blocks up, and then the pressure from the sides keeps them all in there. Okay, jumping back to math. All right, so for this one, Fathom is a computer program that does some statistical analysis. So it is possible that they would give you a data output like this. So what they're telling you here is this first one, the 29.4846, that's your mean. 50 is the count, so that's telling you how many things were in the sample. 0.0900247 or 74, sorry, is your standard deviation, and 0.0127318 is your standard error. Your standard error is your standard deviation, your SX, divided by the square root of n. And that's what A is asking us. A is asking you to interpret the standard deviation and the standard error. Just know your standard deviation is your SX, and your standard error is, so this is SX, and your standard error is SX divided by the square root of n, which in this case would be 50. So since that math's already been done for us, we can kind of just go ahead and jump straight in. All right, so letter B is asking, do these data give convincing evidence that the mean width of cubes produced this hour is not 29.5 millimeters? Use the significance test with an alpha equal to 0.05 to find out. All right, so I've said a couple times in this problem, we're dealing with a two-sided test, and this is why. In part B, they're not asking us if the cubes are less than 29.5 millimeters or larger than 29.5 millimeters. It's just asking, are they different? It says, is it not 29.5? So when we get to writing our hypothesis, it's going to be a not equal as opposed to a less than or a greater than. Well, let's start at the beginning. All right, so for state, first we've got to do our parameter. All right, so parameters are mean, and it's going to be the true mean width of the ice blocks produced in an hour. All right, the stat was done for us. So our X bar equals 29.4846. All right, so for our hypotheses, the null hypothesis is that it is what it should be. So mu equals 29.5. All right, and then, oops, I forgot our symbol. And then our HA is that our mu is not what it should be. So not equal to. Almost everything is going to be the same until we get to the picture and calculating our p-value. But just good to keep in mind that we're going to be dealing with this two-sided. And then the last thing over here is our confidence level, or not confidence level, I'm sorry, our significance level, which is our 0.05 that we pretty much always use. All right, so that's our state. Next up is our plan. So first off, when we're saying our plan, we have to say what we're doing. So we're going to do a one sample t-test for mean. And then we've got to check our conditions. All right, so first we're going to check random. And they tell us in there they pulled a random sample of 50 cubes. So we're good there. For 10%, we need to have 50 should be less than 10% of the cubes produced in an hour. And then for normal, they don't tell us it comes from a normal population, but our sample size is 50, and 50 is bigger than 30, which is our central limit theorem, so we're good to go. So we meet all of our conditions, so then we can jump down to the do. All right, so it's our test statistic equals our stat minus our null over our standard error. And so that symbol, or I'm sorry, as symbols, that would be t equals x bar minus mu. And in this case, we already know our standard error. So if you want to write the formula, you can, but we've already had the calculations done for us, so we can just plug in that number. So our x bar was the 29, and since they're giving us everything, we should use all of it. Our mu is 29.5, and then our standard error is the 0.01. So when you do all of those calculations, you're going to end up with a t-value of negative 1.210. Okay, so we found our t-value. So now we need to draw our picture and then find our p-value. So this one's got a little more depth to it when we're drawing the picture. All right, so first off, we know it's a t-distribution, which looks like a normal distribution. And we had 50 in our sample, so 50 minus 1 is 49. All right, 29.5 is our mean. So what we have for our x bar is 29.4846. So that's here. All right, we also need the other side of that, because this is a two-sided distribution, or a two-sided test that we're figuring out. All right, so you can probably get away with just drawing that. But if that's going to stress you out and you want to figure out what that number would be right here, it's super easy. You just go through and subtract these two. So 29.5 minus 29.4846. All right, so we get that decimal. We're going to add it to the 29.5. So we can figure out this distance over here, because they need to be mirror images of each other. So we're going to end up with 29.5154. All right, so there's our picture. What we're going to do for our p-value is we're going to find this side, and then since both of those should be the same thing, we're going to multiply our p-value by 2. And that's going to give us our actual p-value for this test. So p-value equals our t-CDF, which is lower, upper degrees of freedom. So t-CDF, we're just doing the one side, so negative 99999. And then our upper is our t-value, which that's why we went through all that work to get that. So negative 1.210, and then our degrees of freedom is 49. So we come back over in our calculator, menu, stat, distributions, number 5, lower bound is negative infinity, or negative 9999, then our t-value, and then 49. So we end up with 0.116. So that's the p-value for that one side. So we do need to multiply it times 2. So 2 times our p-value is going to be 2 times 0.116. And when we get that, we're going to get 0.232. Now at that point, hopefully you're going, there is a big problem. 0.232 is nowhere close to 0.05, so we have to fail to reject this, which is actually good. If we're failing to reject, it means we think the machine is working correctly. There doesn't appear to be a problem. The machine is calibrated right, and the foreman in the plant can let things keep going. All right, so conclude. All right, we fail to reject. Because our p-value is not smaller than our alpha. We do not have convincing evidence. All right, folks, so that's it on significance tests for one sample. So for the two sample stuff for means, you're going to hear a different voice. It's the folks that I work with that I get some of my notes from, and the ones that are running the review that we're going to use. So I wanted to go ahead and let you guys start to get to hear them a little bit. They do things slightly differently than I do. I'll make sure if there are any questions that I'll help you out and show you some calculator steps. But I thought it would be nice to hear a different voice for a change, and also just to get you used to those folks as well. So if you have any questions, shoot me an email, come find me in office hours, and hopefully I will see you guys Monday night at 8 if you're available, and if you're not, please make sure you go watch that video once I post it. Thanks everybody. Have a good day.